a relationship where efforts can be summed up. Okay, so it's not necessary. You could have also had another bond like this. Let's say effort 5 flow. In this case, the incoming bonds are effort 5 flow. So this becomes effort 5 plus effort 1 is equal to effort 2 plus effort 3 plus effort 4. Okay, so for a one junction, it is a common flow junction or an effort summing junction, and you can just see that we can write, suppose I am interested in writing effort 3 in terms of the other efforts. You can just see how it can be written. Effort 3 is going out from here. Okay, so this can be written as all the bonds that bring in the effort 1 plus effort 5 minus effort 2 minus effort 4. It is the same equation as before. You just have to understand how to orient yourself. Okay, it depends upon how you wish to express it. So this is as far as the one junction is concerned, the grammar for the one junction. And so whenever the one junction comes under a proper causality, any one bond can bring in the information of flow, say this one. All the other bonds have to accept it. Okay? In the same way, we have the zero junction, and in this zero junction you can see there is a suffix E, and here we have all the bonds that are connected to the zero junction have the common effort. Okay, and only one bond, by the same logic that we applied to the one junction, if we are to avoid any clash among the bonds, then naturally it is necessary to have a constitution for the zero element, and that is that only one bond should be bringing in the information of effort. All the other bonds should accept that information of effort, and so we can just accept this. So you can see that in this zero junction, only one bond is bringing in the information of effort. All the other bonds are accepting it. Okay, so in this sense, the causality of the zero junction is respected. So this is as far as the causality of 4 of the elements of bond graph. Let's see also, of course, we just spoke about causality, but what about the constitutive relations for the zero junction? Just like you have the one junction, here you have for the zero junction
ਪੰਜਾਬ ਗਵਰਨਮੈਂਟ ਦੇ ਕਿਸੇ ਵੀ ਦਫ਼ਤਰ 'ਚ ਭੇਜ ਦਿੰਦੇ ਡੀਸੀ
So for the zero junction, you may have bonds like this. Just for a change, I am bringing in 2 bonds, bringing in power. Let's say this is bond number 1, 2 and 3. For a zero junction, the effort in each of these bonds is the same. So here you have effort, this is effort and this is effort, and flows are different. So flow 3, flow 2 and flow 1. Okay, so you can see here that just like the one junction, the zero junction doesn't retain any power with it. Whatever energy comes in, it gets distributed. Okay, and so you apply the same rule, power 1 plus power 3. In this case, this is the power coming into the system, into the junction, and that is equal to the power, in this case, leaving out from the junction. And so you can write it as effort into flow 1 plus effort into flow 3 is equal to effort into flow 2. And so it becomes also a flow summing junction, okay, where flows can be algebraically added. So a zero junction is a common effort junction or a flow summing junction, okay. So let's proceed with the next. So the rules are well laid down for the one junction and the zero junction. Now let us study
ਪੰਜਾਬ ਦਾ ਬੱਚਾ ਪੰਜਾਬ ਕਰਕੇ ਕਰਦੇ
causality for the I element and also the constitutive nature of the I element. What is it? As an example, let us take a mass and we assume that this mass has a motion v. It has a velocity of v in one direction, and we represent this element, we put an I element here
ਗਵਰਨਮੈਂਟ ਦੀ ਜਿੰਨੀ ਭਰਤੀ
representing this inertia. There is a power bond connected to it, and the effort in this I element is the rate of change of momentum always, okay. In different energy domains the effort element would be different. In case of the electrical domain, you would have rate of change of the electrical momentum L into I, okay, which is the flux linkage, and you would have flow in this case in the mechanical domain as effort. Let us just so here we have this subsystem, we have the I element here, and we are bringing in input to this I element as effort, okay. This effort is resulting in the rate of change of the momentum associated with the I element, and it becomes the input to the I element, okay. What does the I element do? The I element, it is supposed to have the variable, the state associated with it is the momentum, okay, and it is supposed to just obtain this momentum by integrating this effort. So whatever effort was applied to the I element, it resulted in the change of the momentum of the I element. What the I element did is it determined its momentum by just integrating, okay, and it has to provide an output. It provides an output which is the output of the I element, which is a function of the momentum which it has obtained by integration of the effort, okay. So the output or the effect is actually obtained from the cause by integrating the cause, okay, and producing a function which is dependent on the momentum. So if you write it like this in terms of output, you can see that you have the output which is flow. Flow can be written as a function of the momentum, okay. In the case of the mass, when we consider Newtonian mechanics, we consider it as a linear function of the momentum. So we just have momentum divided by mass and it gives us velocity. But we know that we don't have to do this when we deal with relativistic mechanics, where it is no more linear, okay. But anyway, just as a simple example here, we will take this as momentum upon mass, and this is equal to 1 upon m. And how is momentum obtained? By just integrating the change of momentum. Okay, and this is equal to 1 upon m integral. What was the rate of change of momentum? It was the effort that was applied. Okay, so it is just integral of the effort. So you are integrating the effort up to the present time, okay, and you are taking into account the entire past history of the effort. In this case, effort is the cause, okay. You are taking the complete past history of the cause up to the present time, and naturally your effect, it depends upon the past history of the cause. Okay, this is quite natural and this is quite understandable, that if you have something, if an effect is produced, it cannot be on account of a future cause, it has to be dependent on the past. This notion of causality is called as the Galilean notion of causality, where the past effects, causes are taken into consideration in order to produce a current effect. Okay, so this is, now naturally you can see that the causal stroke has to be placed here. I hope it's clear to you. If the input to the I element is taken in this manner, if effort is applied as an input to the I element, then naturally the causal stroke will be placed here. Naturally it will produce a flow. Okay. Now here you are dealing with an integral function. You are dealing with an integral operator, integrating operator. Now what is this actually? What is the property of this operator? You can see that it has an ability to remember the past. You are integrating from some initial time to the present time. That means you are taking into account, you are keeping a track of the past cause, okay, and you are continuously accumulating that. You are just integrating. Integration is just like a cumulative operation, okay. It's just storing this, and then it is producing an effect, which is momentum, and it is producing an output which is a function of that momentum. This is the natural behavior of an inertial element. Okay, it may be in any energy domain. It may be in any energy domain, electrical, mechanical, or any energy domain. You will always find that the cause-effect relationship for an I element naturally is like this. Okay. So you can see that the effect is a function of the integral of the cause. Past cause history is taken into account. You can also write the same thing in this fashion. This form of causality, where the stroke is placed near the I element, is also called as the natural or integral causality for an I element. Okay, and you have other examples of the I element. Just as an example, I'll show you here. You can